Hi everybody, welcome to the first day of chapter 4, which you're going to love because it has a ton of word problems. We have an experienced calculus student here to give you a little feedback about chapter 4, related rates.
Oh yeah, related rates. Those are the best.
They're word problems, right?
Oh yeah.
Optimization.
Yeah.
Don't ruin this. Oh my gosh, be careful. He's ruining everything. Anyway, he's going to help me out with my lesson today and make sure that I keep on track and don't talk for too long. So, Jeff, what do you know about the extreme value theorem?
Ooh, the extreme value theorem has to do with... Wait, what class is this one?
BC Calculus.
Oh, BC.
I mean, AB Calculus.
I
mean, my students should be in BC because they're way smarter than you, obviously.
Relating the rates of the derivatives?
Wow, struggling right there. Okay, so the extreme value theorem is just this theorem that is kind of stupid in calculus, but it's like, oh, it's one of these things that they really break it down way too much and take themselves way too seriously. So two conditions have to exist. You have to have a continuous function, which is basically what you need for everything to exist in calculus, and you need to have a closed interval. Is this looking familiar to you yet?
Yeah.
So if these two conditions exist, then you are guaranteed what?
You're guaranteed to... Oh wait, no, it's a mean value theorem.
Whoops, not an extreme. An absolute maximum. Max. Oh, he's mumbling now. And an absolute minimum. Okay, so it seems kind of obvious why they have to just completely say like, oh, it's so fancy, the extreme value theorem, but let's take a look at it. So if I have a function like this, some sort of cubic function, you can see that because it goes on forever in both directions, that it's not going to have any extreme maxes or extreme minimums. But if I look at this point right here, I could say, oh, this point is a local maximum because it's the biggest value around relative to that. And this point, I would call this a local minimum because it's the lowest value relative to the points around it. Now, these are also called relative minimums, depending on what books you read, and relative maximums. Now, the reason why the extreme value theorem didn't give us any absolute maxes and absolute minimums on this is because it's not on a closed interval. It goes on forever. So now if I say, oh, what if I take that function and I just write a specific part of it like this? Just take this piece here. Well, now I have a closed interval. So I would say that this right here is my absolute max. And then this piece right here is my absolute minimum. So this happens somewhere inside the interval, and this happens at the end of the interval, and that's okay too. So what the book wants you to do is look at a bunch of little pictures and just identify the absolute max and min. And if you can't identify the absolute max and min, why is it doing that? Strobe light. If you can't identify the absolute max and min, then you have to say why. Okay, I hope the batteries aren't dying on that thing. So let's look at this. Oh, wait. Okay. So as I look at this function, I'm over here. This part up here, I can say that this is the absolute maximum. But this down here, even though it's below this point over here, I can't say that this is the absolute minimum because it's on an open interval. It never actually gets to this point right here. So we only get the absolute max because we're not on a closed interval. We're not guaranteed to have an absolute min. But if I said, oh, now this is really a point, then you would say, oh, okay, great. Now you're on a closed interval, so you get both the absolute min as well. Very exciting. Now, the more interesting part about your section today is how to actually identify where those absolute maxes and absolute mins are. I should have left that there. So if I look at this graph, like I just erased, and I'm going to redraw it, if I try to find these mins and maxes, what do I know about the tangent lines right here?
Slope is 0.
Oh, what? The slope is 0. So that means what's going to happen at these points? The derivative will be equal to 0. The derivative will be equal to 0. So you can identify all of the maxes and minimums. And we have a new word that we're going to start talking about, and it's called critical points. We'll talk more about critical points in the coming up section, but all that critical points are is anywhere, do you know this?
Anywhere where the first derivative is equal to 0 or undefined.
Oh, you got it. Anywhere where the derivative is equal to 0 or does not exist. Okay? And so in the future, where the critical points are going to be really important to us, they're not always going to give you maxes and mins, but they are going to give you some very important information. So let's try an example. Let's see, I have it written down on this paper. I couldn't remember it. Okay. This is, I promise, is all that I'm going to do 2 examples. So, y is equal to x cubed minus 12x plus 4. I know that that's a cubic, so it's going to look something like this. And so maybe I'm going to have 2 maxes and mins. Or maybe it's one of the cubics that's just going to do something like that. In which case, I'm not going to have any maximums or minimums. So all you have to do is take the derivative. So, oh, look at how nice this is to take the derivative of. 3x squared minus 12. And since I know the slopes of all maxes and mins are going to be equal to 0, all I have to do is set this equal to 0. So 3x squared equals 12. X squared equals 4. So x is equal to plus or minus 2. So that means that I'm going to have a situation that looks something like this. At negative 2, I have a max. And at positive 2, I have a min. And the way I figure out what the y values are of these points is I just go back and plug them back in there. So I already did that. It's like a cooking show. Look at how great it looks when I take it out of the oven. So 2, negative 19. And you can put this in your calculator and check it and make sure that's right. So basically, we are able to find those maxes and mins without using that max min feature on your calculator.
What about the first derivative test?
We're not there yet. He's trying to give you too much information. Okay. Let's do one more example, then we're done. You're probably really bored. Oh my gosh, it's not even here. Okay, I'm making one up. So y is equal to the square root of 3, or let's say 4x minus x squared. Okay, so this derivative is a little bit harder to take. So 1/2 times all this stuff raised to the negative 1/2, and then times by everything inside the derivative of what's inside here, so that's 4 minus 2x. Now here's where your algebra skills have to be pretty good, because I can write this as 4 minus 2x, all of that divided by 2 times the square root of 4x minus x squared. And I'm going to set that equal to 0. So if I'm setting this equal to 0, the denominator can never be equal to 0 because it's undefined. So when I have fractions, all I have to do is worry about the numerator, which is a lot easier. Yay, we don't have to worry about that. So 4 minus 2x equals 0, so x equals 2. And then if you wanted to find the y value of where the maximum is, 4 times 2 minus 4, so that's 8 minus 4. Oh my gosh, look, it worked out perfectly. Square root. So the maximum is at 2, 2. So put in your graph, in calculator, check it out, make sure that we're correct, and then you guys can get started on your homework, and I'll see you on Monday. Say bye, Jeff.